Hello everyone, this is Dilip. In this video, let's look at backpropagation algorithm. This we'll use to solve our neural networks hypothesis. This is one of the most difficult videos to make, so the content is very complex. I tried to simplify as much as possible. Please let me know what you think in the comment section after watching the video. In the earlier video, we have seen how we have derived the hypothesis for neural networks. The link for this I'll leave in the description. Based on the input features, we derive the features of this layer, and based on them, we have derived the final hypothesis. As you can see, we are moving forward in this for calculating the features in between layers, and finally to calculate the hypothesis. And the final hypothesis looks like this. And as part of the notation of activation nodes, we can also represent hypothesis as A21, where this 2 indicates the second layer and 1 is the one node. For a multi-class classification problem, we will have multiple hypotheses. So this can be determined as the sigmoid of the parameters applied on these features. So these parameters and weights I'll use interchangeably, but both mean the same thing. So here you can see in forward propagation, we are calculating the activation function. And to solve the neural networks, we'll see how to do the backward propagation as well in the later slides. So moving on, this is the logistic regression cost function. And based on that, we have derived the cost function for neural networks. Earlier, we have seen in logistic regression as well, for the optimization algorithm, the requirement is we need to give it some code to calculate the cost function g of theta as well as derivative of the cost function. And then this optimization algorithm can take care of calculating the optimum theta values. So we have already seen the cost function equation, which is this one. So using that, we can calculate the cost function. Now, how to calculate the derivative? For this, we use the backpropagation algorithm. Let's take our earlier example where we have the hypothesis already. And as you can see, these theta parameters are the weights for the input features. And using them, we have the hypothesis. So let's represent our hypothesis in our activation function. And then this is the error. The error at this neuron is represented by h of x, which is nothing but a2 of 1 here, minus expected result. So this is the calculated hypothesis value output, and this is the expected result. And if you represent it in vector notation, so if you have multi-class classification problem, we'll have multiple hypotheses and multiple output error values. And if you input in vector format, so this is for layer 2, the error value is the hypothesis calculated layer 2 minus expected test result, which is y. So now we have the error calculated at layer 2. Similarly, if you want to calculate the error at this layer, at layer 1, what we do is we take the error value to be theta 2. Theta 2 is nothing but the weights at this layer, in between this layer and this layer, transposed with and multiplied with error value at the next layer. So error value at this layer multiplied by G prime Z2. So this Z2 is nothing but this value. So G prime is nothing but we are calculating the derivative of the sigmoid function. So the derivative of sigmoid function is it multiplied by 1 minus itself. So G prime Z2 is nothing but the value of A2 here multiplied by 1 minus A2. So using this, we can get the error values at layer 1. So this one, at this layer also, we got the error value. And once we get the error value, the delta at a particular layer for the particular theta parameters ij is ALJ, which is nothing but the activation node output for the particular neuron multiplied by error in the next layer. So the first thing is we need to calculate the error in the next layer. What is this delta and all? It will be clear in the next slide. But the first thing is we need to calculate the error in the next layer. The only way to do it is if we come in the backward direction. In this way, it is possible to calculate the error of the next layer in advance when moving backwards. So let's see. Ultimate goal of this back propagation algorithm is to derive the derivative of the cost function. So this is the ultimate goal. Not to solve the neural networks, but to get this derivative. Okay, let's move on. Initially, we'll initialize all delta Lij to 0. So each delta Lij corresponds to theta parameter in the neural network. So there is a delta Lij corresponding to this, there's a delta Lij corresponding to this, like that. There's a delta Lij corresponding to this, like this. Okay. So usually for the first layer, we don't calculate like this is the, for this layer, we don't calculate what are the parameters available for the input layer. We don't calculate the error. So we don't calculate error at this layer. So just for all the weights which are shown in the from the second layer and forward, we will have a delta. So initially we will put all delta to 0 and iterate through all training samples. So this is like a for loop where we go through all training samples. And for each training sample, what we do is we perform forward propagation and compute AL. It means the activation function output for each layer. And then what we do is by iterating backwards, we calculate this value, which is nothing but the delta values. So initially, this delta will be 0. And this value will be for the next layer. And second time, for the second training sample, when we come, that time this delta Lij will be pre-filled. So this delta Lij will keep adding up all the error values together for a particular weight or for a particular theta parameter. And dj by d theta for the particular layer for a particular theta is 1 by m times delta of Lij plus lambda multiplied by theta of Lij. This if we have regularization when I not equal to 0. When I equal to 0 means for the bias parameter, since for bias parameter we don't have the regularization, we get it simply like this, dj by d theta. And in this way, we calculate the derivative of cost function with respect to a particular weight. So now we have seen how to calculate the cost function and the derivative of the cost function for each weight. So we can use any optimization algorithm now to solve neural networks. We can go with stochastic gradient descent or Adams classifier or any other optimization algorithm. I have listed these two because these are the most famous ones which are being used for classification problems when using neural networks today. So thanks everyone for watching the video. Bye. Have a great day.